So welcome back. I've already introduced Scott, so I won't introduce him again, and we'll get to it. Scott?
Okay, so this is a talk on the what we know about supermassive black holes. I feel obligated to start by stressing that these are not LIGO black holes. The general categorization is that we have three categories of black holes. The stellar mass black holes, less than about 100 solar masses, where solar mass is 2 × 10⁻30 kilograms. These are the ones that gave rise to the famous LIGO gravitational wave event. There's intermediate mass black holes between 100 and up to about 10⁵ solar masses. The existence and properties of these are still very much in doubt, so I'm not going to talk about these, and I'll focus instead on the supermassive black holes, even though I hate the name. Anyway, they're always called supermassive black holes, and they're between 10⁵ and 10⁻⁻⁰ solar masses. So an example is in this galaxy. This is the M31 or Andromeda galaxy, nearest large one to our own. The scale here is about 3 kiloparsecs, where a kiloparsec is 1,000 parsecs, and a parsec is 3 × 10⁻¹8 centimeters. In this image, there are believed to be 2 supermassive black holes, one in this satellite galaxy, M32, with 3 million solar masses, and one at the center of the main galaxy of about 10⁸ solar masses, which I'll say more about in a few minutes. So the original evidence for supermassive black holes came from trying to understand quasars, which are the most luminous active galactic nuclei. They emit up to 10⁻13 solar luminosities, which is between 100 and 1,000 times a typical galaxy luminosity. A reasonable, very plausible upper limit to the luminosity of any object is the Eddington luminosity, which is the point where the radiation pressure on a proton due to Thomson scattering exceeds the gravitational force on it. That luminosity is written as a formula that just involves the mass of the central object, proton mass, and the Thomson scattering cross-section, and it comes out to 3 × 10⁴ solar luminosities times the mass in solar units. If you then put in this extraordinarily large luminosity, you conclude that whatever the object is that's powering the quasar, it has to have a mass of at least 3 × 10⁸ solar masses. And for a variety of reasons that I'll now describe, most astronomers are convinced that the energy source for not just quasars, but all active galactic nuclei is accretion of material onto a black hole. If it is a black hole, then just for reference, if the mass is 10⁸ solar masses, the Schwarzschild radius is about twice the Earth-Sun distance. So that's, of course, large on solar system scales, but extremely small on galaxy scales. So let me just quickly go over some of the evidence for this statement that the energy source for all AGN is accretion of material onto a black hole. One is the presence of radio jets. This is an example of a radio jet around the radio source Cygnus A. You can see on the very largest scales, 50 kiloparsecs, you can see 2 large lobes of hot gas emitting in the radio, and you can barely see a jet going from this active galactic nucleus in the center. If you go down to much smaller scales, 50 parsecs or even half a parsec, you can see that the jet is oriented in the same direction. Since even traveling at the speed of light, it takes about 10⁵ years to get out to 50 kiloparsecs. That means that whatever the source of the jet is, it has to maintain its directional stability on 10⁵ year timescales, And a very natural way to do that is by a spinning black hole. This is a second jet on a much smaller scale and in a much more nearby galaxy, N87 in the Virgo cluster. This is millimeter wave images of the jet over a period in 2013 and 2014. You can see that one of the blobs in the jet is expanding. It's apparently expanding at close to the speed of light. The only plausible way you can, it actually appears to be expanding faster than the speed of light. That's a special relativistic effect that occurs if the actual motion is close to the speed of light. The only way we know of to accelerate things up to the speed of light is in a relativistic potential well, and the only thing we know of that has a relativistic potential well is a black hole. So that's a second piece of indirect evidence. A third is the very small size of the quasars. Some active galactic nuclei have time variability on timescales of only a few weeks. It's extremely difficult to build a model of an astrophysical source that varies strongly if the size of the source is bigger than the light travel time on that timescale. And that suggests that the size of the emitting region is less than c times a few weeks, or about 2 × 10⁻16 centimeters. Again, that's about 1,000 times the Earth-Sun distance, but many orders of magnitude smaller than the size of the galaxy. And it's very hard to invent any source that can emit this much luminosity and be this small other than a black hole. You can get even better limits on the size from gravitational lensing. This is a famous gravitational lens called the Einstein cross. These are 5 images of a single background galaxy that happens to be aligned with the center of the mass distribution of an intervening galaxy, which is creating the 5 separate images by light bending. Each of the images, each of these 4 images, the brighter ones, varies substantially and independently. And the most natural model for this is that the images are being brightened by gravitational lensing from individual stars in the intervening galaxy. In order for that to happen, the source size has to be smaller than a characteristic Einstein radius around the intervening star, and that implies a size for the quasar even smaller, less than 10⁻14 centimeters. And again, it's very hard to find a model that can emit this much energy in that small a size unless it's a black hole. There's also evidence from the X-rays. This is X-ray emission spectrum. The line is 25 times ionized iron, so it's hydrogenic iron. There's the rest wavelength. The existence of this long tail towards lower energies is believed to be due to a combination of gravitational redshift and Doppler shifts from relativistic motion in a disk. And since, as you can see, the spread of the line is comparable to the original energy, this requires that both the gravitational redshift and the velocities are coming from a relativistic potential well, and the only thing we know of that can produce that well is a black hole. The final argument I'll give is that for any energy source, there's a natural dimensionless efficiency, which is the ratio of the energy it produces to the rest mass energy of the fuel that it consumes. For nuclear reactions, the efficiency is somewhat less than 1%, but for accretion from a accretion disk onto a black hole, the efficiency ranges from 6% up to a maximum of over 40%. The fuel requirements to produce the energy emitted by quasars over their lifetime are so large that with efficiencies even as large as you get for nuclear reactions, the fuel supply is comparable to the supply of gas in the entire galaxy surrounding the black hole. So in order to have an adequate fuel supply, you really need much higher efficiencies. And the only thing we know of with much higher efficiencies in the percent to 10% level is accretion onto a black hole. So those are extremely simplified summary of the arguments for black holes as the energy source for quasars. I just want to point out a couple of other pieces of physics associated with the quasars. The first is that if you emit a certain amount of energy with this efficiency, you also produce ash, you produce residual material, which means that the black hole mass has to grow by a ratio which involves the 1 minus the efficiency and the efficiency. So the less efficient you are, the more mass you have to add to the black hole to produce a given amount of energy. The second piece of phenomenology I wanted to point out is that quasars aren't uniformly distributed over the age of the universe. This is the rate of burning of fuel associated with quasars and solar masses per year as a function of either redshift or time from the Big Bang. And you can see that the peak of the quasar activity was at a redshift around 2 at about a quarter of our current age of the universe. And at the present time, the co-moving luminosity density of quasars is a factor of 1 to 2 orders of magnitude smaller than it was in the peak. So quasars are really a phenomenon that is concentrated in the relatively early universe. And with those bits of physics, you can make a very compelling and interesting argument. If you believe that supermassive black holes are the power source for quasars, and that you recognize that the present co-moving number density of quasars is much less than it was at earlier epochs, and that quasars are found in galaxies, then it has to be that many nearby galaxies contain dead quasars, quasars that were active at redshifts of 2, but are now dead, presumably because they're starved of fuel. So many nearby galaxies have to contain supermassive black holes that are hard to find because they're simply not shining. You can make that argument quantitative because since the universe is homogeneous, you can add up the local density of quasar photons. If you know the efficiency, then from this formula you can calculate how much ash is left over. The ash is going to be in the form of inert black holes, and that gives you an estimate for the total density in solar masses per cubic megaparsec of black holes left in the early universe. Sorry, black holes left in the current universe. The final piece of physics that I'll provide in this introduction is that we believe dead quasars ought to be found not just in galaxies, but at the centers of galaxies. There are a couple of reasons to look at the center for the dead black hole. One is that that's the bottom of the galaxy's gravitational potential well, and so it's natural that gas and other material would accumulate there. The more prosaic reason is that that's the only place we can easily find them. If they're out somewhere else in the galaxy, they're going to be very hard to find. And the strongest reason is dynamical friction, which will cause the orbits of massive bodies to spiral to the center of the galaxy. Dynamical friction arises simply because if a massive object is traveling through a sea of background stars, as it goes past, its gravitational force will attract the stars towards it. Most of that attraction will lead to a density enhancement or a wake behind the massive body. That exerts a gravitational force on the supermassive black hole and steadily drains energy from its orbit. You can work out how fast that energy drain should be. Again, in the Andromeda galaxy, 10 to the 6th solar mass black hole would spiral to the center from here, 10 to the 7th solar mass black hole from here, and a 10 to the 8th solar mass black hole from almost anywhere in the visible galaxy. And so it's very plausible that black holes with this kind, even if they were born somewhere in the outskirts of the galaxy, would by now be at the center. So that's the place to look. With that introduction, let me try to summarize the evidence we have that there really are such objects in nearby galaxies. The first and most famous example, of course, is our own galaxy. This is a picture of the central regions of the galaxy taken in infrared light. This is about 1 kiloparsec. For comparison, the sun's about 8 kiloparsecs from the center. The central region of the galaxy, we've been slow to learn about simply because it's heavily obscured by dust, and it's only with the development of infrared technology that we've been able to examine it closely. This is a much magnified view of the central parsec of the galaxy. Right at the center is a strong radio source called Sagittarius A star, and my contention will be that Sagittarius A star is a black hole. The strongest evidence for this, I think most of you have seen, is high precision astrometry of infrared observations of stars near the center, which have enabled tracking the orbits of stars. This has been done independently by two groups, one led by Andrea Ghez at UCLA and one by Reinhard Genzel in Munich. And it's impressive that both are getting very similar data. The most interesting star and the one with the shortest orbit is this one, which has now followed over a complete orbit. And it's clear that all of these stars are orbiting around a massive object somewhere in the center of these orbits. More specifically, the orbits can be fit to Kepler ellipses. The center of attraction of the Kepler ellipse can be determined, and it coincides with the radio source Sagittarius A star, which is why we think it's the black hole. The smallest pericenter of any of the orbits is this one, and it's only about 3 times the Neptune distance. And the smallest orbital period, again, of this one is 16 years. All of the orbits, including this one, are closed Kepler ellipses, and that says that the mass that they're attracted by must be contained within the pericenter of the orbit, which sets an upper limit to the size of the mass of a few times the distance to Neptune. You can also determine the mass of the central object, and with a precision of maybe 5%, it's about 4 million solar masses. The observations also, incidentally, give the best determination we have of the distance to the galactic center. So the galactic center contains 4 million solar masses in an area, in a volume not much bigger than the solar system. If you try to think of alternatives to a massive black hole that could provide this mass in this volume, they're all very short-lived. So for example, a cluster of neutron stars will only survive for a tiny fraction of the age of the universe. The only long-lived alternatives are extremely implausible. You could have a cluster of 10 to the 10th planet-sized black holes. You could have a Bose-Einstein condensate of some unknown elementary particle. But I think these are reasonably safe to discard, and that means that the only long-lived alternative that's left is a 4 million solar mass black hole. We will hopefully learn more about this in the next couple of years. Sagittarius A star does emit synchrotron radiation from the accretion flow onto the black hole. The emission is supposed to be concentrated near the Schwarzschild radius of the black hole, which for the mass I've given is about 10 to the minus 5 arc seconds. And surrounding the Schwarzschild radius, there would be a shadow whose size should be about 2.5 times the Schwarzschild radius. It is now technically feasible to see that using global interferometry of millimeter wave radio telescopes. A collection of these has now been called the Event Horizon Telescope, and they're engaged in the extremely challenging task of coordinating observations on a diverse set of telescopes and beginning to analyze the data They have preliminary experiments that are already resolving maybe 100 Schwarzschild radii. They expect to get the first images, which simulations show could look like this within the next year or two. And if you can see an image like that, it would effectively be an image of the first image we have of the event horizon of a black hole. The second unusual way to try to explore the black hole in the galactic center is a phenomenon called hypervelocity stars. These were predicted by Hills back in the 1980s, who pointed out that there are plenty of stars close to the black hole in the galactic center. If a tightly bound binary star comes close to the black hole, it can be tidally disrupted, and then one star of the binary will be flung out with much higher velocity than it originally had. He argued that without knowing much about the parameters of the black hole, that the ejection velocity could be up to 4,000 kilometers a second. That seems a little high, but it could easily be 1,000 kilometers per second. In fact, the maximum ejection velocity scales roughly as the orbital speed of the binary times the ratio of the black hole mass to the mass of the stars to the 1/6 power. So if you're looking for a challenging mechanics problem for one of your courses, this is a nice one to try. So the picture you should have is that from the center of the galaxy there will be a slow but steady stream of stars being shot out radially from very close to the black hole, speeds between 500 and 2,000 kilometers per second, much larger than the typical speeds in the galaxy, which are 100 or 200 kilometers per second. The way to find these is to look for stars that are high above the galactic plane, because then there's less confusion from other stars. You can look for young stars because those are the brightest, so they're easiest to find, and they're also distinct from the other stars in this halo region because they're all old. It has to be moving at high radial velocities, and of course if it's at large distances, they have to be traveling away from us. And it's pretty clear that these have now been found. This is from a survey of distant stars in the galactic halo. You can see these are the radial velocities. Negative means moving towards us, positive away. The velocities are such that in a frame which is the rest frame of the galaxy, so 0 would mean at rest relative to the galaxy. You can see that most of the stars are roughly fit by a Gaussian, but beyond the Gaussian there are tails. In this case, coming towards us, the tail contains only 2 stars. Going away from us, the tail contains 26 stars, and most of these are probably hypervelocity stars ejected by the black hole in the galactic center. They satisfy a number of tests. The velocities are much higher than the only other competitors, which are stars produced if a supernova goes off in a close binary. Those are typically less than 200 kilometers a second. The travel time for the stars from the galactic center has to be less than the stellar lifetime, so they could be formed in the center. That seems to be true for almost all of the ones that have been discovered. The rate is about 1 star per million years. That's consistent with the theoretical predictions. The velocities are outward. The number inside some radius goes roughly as the radius, which is what you would expect for a uniform ejection rate. It's much less clear whether they're isotropically distributed, which is what you would expect on this model, simply because the surveys don't cover the whole sky. We'll know more once data comes back from the European Space Agency Gaia spacecraft, because it'll measure proper motions, angular speeds across the sky, and then the velocity vectors should all point away from the galactic center. So we have the potential to learn a lot more, but the evidence for a black hole at the center of the galaxy is now extremely strong. The next largest galaxy is the Andromeda galaxy. It's important because it is the next large galaxy after the Milky Way. So the angular size of the region where the black hole dominates the gravitational potential is bigger than in any other galaxy. And in contrast to the center of the galaxy, there's little or no gas, dust, recent star formation. It has a very clean center, so the distribution of stars is easy to interpret. This is what the distribution of the stars looks like in the highest resolution image we have from the Hubble telescope. It has this curious feature of a big lobe of stars out here, traditionally called P1, a small lobe of stars here, P2, and then a little blue point source here. The interpretation of this is that there is a supermassive black hole right at P3, and that the blue point is a very compact disk of young blue stars surrounding the black hole. That there's also a larger disk of older reddish stars. Because of the gravitational field of the black hole, the gravitational potential is Keplerian. The orbits are eccentric. Keplerian orbits don't precess, and so these happen to be aligned so that their long axes are all pointing in the same direction. This is the portion of the disk close to apocenter where the stars move most slowly. They linger here the longest and produce most of the luminosity. On the other side is pericenter. The stars are moving quickly and they don't produce much luminosity. This may sound like a contrived model, but it actually works very well. This is the data. There's a simulation of what the model looks like. It correctly reproduces the photometry. And then if you take this model that's only designed to match the photometry and add one free parameter, that is the black hole mass, you can fit the rotation curve measured as a function of distance away from the galactic center. And that's particularly challenging because the rotation curve is asymmetric. It goes up to only 160 kilometers a second on one side and to 230 on the other side. The black hole mass that you require to fit the rotation curve is 10 to the 8 solar masses. You can do more by looking at the cluster of blue stars. This is very small and right at the limit of resolution of the Hubble telescope, but you can get good spectra from the fact that the spectrum, because the color of these is different from the color of the stars behind, you can take a spectrum of off the blue cluster of the stars behind and subtract that from the observed spectra to isolate the spectrum of the blue cluster. The spectrum looks like this. For comparison, this is an A star where you see the strong series of narrow bomber lines. You see the same lines in the blue disk, but much broader. The broadening is due to the velocity dispersion, which can be fit to be almost 1,000 kilometers a second. For comparison, the velocity dispersion a little further out in M31 is only 150. This much higher dispersion is almost certainly because these stars are orbiting deep in the gravitational potential well of the black hole. Again, you can fit this, you derive a mass of 1.4 times 10 to the 8 solar masses, which is within the error bars of the mass that you got on much larger scales by fitting the rotation curve. So again, I think there's a very strong case that this object has to be a black hole and that we know the mass of the black hole reasonably well. My third example is an otherwise undistinguished galaxy called NGC 4258. The remarkable thing about this is that it has a very compact disk of gas near the center, and the conditions in the disk are such that you get maser activity from the gas clouds in the disk. You get the maser activity where the velocity gradient along the line of sight is small so that you can have a long path length for the maser. You see, so these are maser spots. You get some maser spots here, and you get a couple over here. And when you plot the velocities, you see from the red and blue spots, you see an extremely accurate, quite beautiful Keplerian rotation curve, which tells you that the gas is in a very slightly warped, but otherwise extremely clean disk of gas orbiting on circular orbits around a point mass. You get 3 pieces of information from the masers. From the ones in front, you can measure their proper motion, their motion across the line of sight. You can measure the amplitude of the Keplerian rotation curve, and You can even see drift in the masers in the center, which is arising because of the centripetal acceleration they have around the central object. So you have four pieces of data, 3 unknown parameters, the radius, the distance of the masers here, the distance of the galaxy and the black hole mass. They all fit consistency with the black hole mass of 4 times 10 to the 7th solar masses. That's the most accurate black hole mass we have other than the galaxy, and it also gives you a direct measurement in 1 step of the distance to the galaxy. This is remarkable enough, but due to a major effort, we've been able to find other examples of masers. Here are 2 more with similarly clean Keplerian rotation curves, again giving exceptionally accurate black hole masses with accuracies of better than 10%. And by now we have about 19 good black hole masses coming from a variety of galaxies with maser disks. All of these are somewhat special cases. What you'd like to do is see if there's evidence for black hole masses in general galaxies without masers or without at distances where you can't see the orbits. And that's hard but can be done. Roughly speaking, the way you have to do it is to measure the spectrum of light from the galaxy at a variety of positions. Then you know that that light is composed of stars with some intrinsic spectrum that you know from observations of stars in the galaxy. You assume there's some number of stars as a function of the line of sight velocity, and then the actual spectrum will be the convolution of the intrinsic stellar spectrum with the number of stars as a function of velocity, accounting for the Doppler shift in the intrinsic spectrum. Once you measure this, you can try to invert this equation. It's ill-posed, but at least you can measure the mean velocity and the velocity dispersion at that location. And then if there is a black hole with some mass, it'll influence the kinematics, the mean velocity and the dispersion inside some radius where the gravitational potential energy from the black hole exceeds the kinetic energy. That's conventionally called the sphere of influence. And in order to get a good measurement of the black hole, the crucial thing you need is to resolve the sphere of influence. That is, you're not going to see a strong signal unless you can resolve distances smaller than the distance defined here, and the number of galaxies in which you can detect a black hole goes as the cube of the telescope resolution, because you can go much further out and see many further galaxies. The workhorse for the last 2 decades has been the Hubble telescope, which has a point spread function with a full width half maximum of around 1/10 of an arc second. That's now gradually being supplanted by ground-based telescopes with adaptive optics, which can achieve a comparable resolution. The effect of the resolution can sort of be illustrated here. I've just plotted 3 different typical rotation profiles at various degrees of resolution. If the resolution was infinite, you'd see a Keplerian rotation curve going up to infinity near 0, but the worse the resolution is, the more the rotation curve gets smeared out until here there's no real evidence for a Keplerian portion at all. Similarly, the velocity dispersion, the RMS velocity in the limit of infinite resolution would go to infinity here, and the peak just gets smaller and smaller as the resolution goes down. So that's what you expect things to look like if a black hole is present. That's the models again, and this is just to persuade you that there are cases where you actually see this. Again, in the velocity dispersion, you see this characteristic peak near the center. This is another galaxy with a similar peak from 200 to 300 kilometers a second. The rotation curves here show a hint of the Keplerian rotation here. Here it's less persuasive that it's been resolved, so you're relying more on the velocity dispersion. So with this sort of technique and detailed modeling, there are something like 40 more galaxies with reasonably good black hole masses that can be measured just from the stellar kinematics. So what does all this tell us about the relation between the supermassive black holes and the galaxies? Typically, there's a wide variety of different galaxies, different types of galaxies, and they're roughly speaking divided into hot components, which have relatively little rotation and large velocity dispersion, cold components, which are disks. So here's the hot component. In this case, there's both a hot component and a cold component, or a disk. In this case, the hot component is more modest, the disk is more prominent. This one is edge on, and you can see a small hot component at the center. In this case, there's only a disk and no hot component. The most striking feature of these measurements is first that there's an approximate correlation between the measured black hole mass and the stellar luminosity of the host galaxy that's roughly linear. With a fairly large scatter, the black hole mass goes like the luminosity of the galaxy. Since the luminosity of the galaxy is roughly proportional to the mass of stars in the galaxy, you can say that the ratio of the black hole mass to the mass of the stars is somewhere between 0.2 and 0.5%. The different colors indicate pure hot components or hot components with the disk. The different symbols indicate different methods for measuring the black hole masses, but they're all roughly consistent. Apart from the correlation with the overall luminosity, the other striking thing is that almost all galaxies with hot components do contain black holes. It's not that you look at a bunch of them and you find one 10% or 1% of the time. Every time you look and you think you should see one at about this level, it's present. You can do better by correlating the black hole mass not to the luminosity of the host galaxy, but to the velocity dispersion of the galaxy outside the sphere of influence of the black hole. This is a somewhat tighter for elliptical galaxies. The scatter in the log to the base 10 is about 0.3. That's substantially better than you get with the looking at the luminosity. You can try to, in this case, we're looking mostly at elliptical galaxies, galaxies with hot components. You can extend the, you can extend your search and look at all kinds of galaxies. This is a more recent plot that has somewhat less stringent constraints on the accuracy of the black hole masses, but it has a lot more points. It has close to 200 points in this diagram. And with some exceptions, not these, because these are only upper limits, which are consistent with the relation, there's still a reasonably clean relation between velocity dispersion and the black hole mass. Okay, so what do we learn from this correlation? The first thing is that the masses of the so I've said the masses of the black holes in nearby galaxies are a fraction of a percent of the stellar mass in the hot component. We have large surveys of galaxies that can measure the average mass density in galaxies. And since we have that percentage, we can go from the mass density in galaxies to the average mass density in black holes. You get a number of about 4 times 10 to the 5th in solar luminosities per cubic megaparsec. But you'll recall from earlier in the talk this chain of logic that led to a prediction that the ash left over from the burning of the quasars should be 3 times 10 to the 5th in these units if the efficiency is about 0.1. So if you combine the two, you can see that what we measure in dead black holes in the centers of galaxies and what we predict should be there for a plausible efficiency for the quasars within the errors is the same. This is a plot from an independent calculation by Shankar. The density, because of the quasars are mostly around redshift 2, the expected density of quasar ash goes up as the redshift goes down. Its current value should be roughly around in this range, and that's consistent with what you get from measuring the black holes. So that leaves very little doubt that the objects that we're detecting in the centers of galaxies are the same, are the remnants of the same objects that powered the quasars. Okay, so the implications and the summary of this part of the talk are that we see objects, technically we only know that they're dark and they're very compact. Between 10 to the 6th and 10 to the 10th solar masses, they're present at the centers of most galaxies. Indirect arguments say that they have to be black holes because we can't think of anything else they could be. The arguments I've given based on the energy budget for the quasars strongly suggest that these are actually the remnants of quasars. That tells you that black holes don't grow by merging black holes. They don't grow by accreting dark matter. They must grow mostly during the same phases when the quasars are luminous by accreting gas that glows as it spirals into the event horizon. The fact that there's a correlation between the galaxy velocity dispersion and black hole mass says that there must be some deep connection between the formation of galaxies and the formation of black holes. At first glance, that's a little surprising because the black hole mass is less than 0.5% of the stellar mass in the galaxy. The thing to bear in mind is that the energy that's released in forming the black hole of this mass is some thousands of times larger than the energy released in forming the rest of the galaxy. And so it's, if only 0.1% of the energy released in forming the black hole is fed back into the gas of the galaxy, it has the potential to blow the gas out of the galaxy and quench the galaxy formation. Whether this works and whether there's evidence for it and how it works is one of the hot topics in trying to understand galaxy formation today under the general name of feedback. So I think everything I've presented so far has been, is I think reasonably standard. It's a nice story, everyone agrees on it, and I'd like to spend the last few minutes talking about another aspect of the story that nobody agrees on. That has to do with what's called the last parsec problem. The origin of the problem is we know that galaxies form by hierarchical merging of smaller units. If two galaxies have, we know that most galaxies have black holes. If two galaxies with black holes merge, then after the merger, the black holes are going to be floating around somewhere in the merged galaxy, but because of dynamical friction, they'll both spiral into the center. So you'll have two black holes that are very close to the center, and either they're going to merge or they're going to form a binary black hole. If they merge, they should generate gravitational wave events because black holes are black holes. The events will look exactly the same as this one, except the overall time scale will be expanded by the ratio of the masses, say the ratio of 30 solar masses to 10 to the 8th solar masses. These are remarkable because they're the most energetic events in the universe. They release millions of solar masses of rest mass energy in an extremely short time scale. But because the time scale is much longer than the LIGO time scale, they can't be detected because LIGO has no sensitivity in the relevant waveband. One way they could be detected is through the proposed ELISA spacecraft, which is an ESA mission, hopefully for launching in the 2030s, in which you have 3 spacecraft that form an interferometer. This is slightly over-optimistic. The third arm of the interferometer isn't present, with an arm length of about 1 million kilometers, and each object is freely falling because it has a proof mass inside an isolation chamber at the center of the spacecraft. The bad news is that it's unlikely I'll be alive when ELISA is launched. The good news is that LISA Pathfinder was launched last winter just to test whether they could, the proof mass concept, whether they could create a freely falling spacecraft, and they were able to do so successfully. The second possible way to detect these is through pulsar timing. Essentially, you can measure a stochastic background of gravitational waves due to mergers of supermassive black holes during the in-spiral phase before they merge but when they're in the last stages on orbits with periods less than a few years. And there's a large armada of radio telescopes that are now being used to conduct precise timing observations. Basically, as the gravitational wave passes through the galaxy, it affects each of the pulsars independently, but when it passes by the Earth, it changes the position of the Earth, and that affects all of the pulsars coherently. So the bad news about this is that it's only going to detect probably a stochastic background rather than individual black holes. The good news is that it is almost at the stage where it can do so. The black points and the curves are the current sensitivities of the various pulsar timing arrays, and the colored bands are theoretical models of what the amplitude of the stochastic background should be. So they're already ruling out some of the models, and within the next 2 or 3 years, the observation should have improved enough that either there will be a detection or there's some problem with the models. And what I'd finally like to talk about is the possibility that there is a problem with the models. All of these models assume that when the black holes get close enough, they will eventually merge. And it's not so clear that that's going to happen. This was first pointed out in an important paper by Begelman, Blanford, and Rees. And the reason for the uncertainty is that the final stages of the merger are extremely complicated and difficult to understand. As I've said, you start with the black holes spiraling in from the outskirts of the galaxy through dynamical friction. As they come to smaller and smaller radius, eventually they'll form a bound pair. As they continue to spiral, because they're on a Kepler orbit, the velocities are going to increase. So there'll be more dynamical friction, but eventually the Keplerian velocity of the black hole will become bigger than the velocity of dispersion of the stars it interacts with. The binary will be said to become hard. At that point, because of adiabatic invariance, the interactions with the stars become much less effective. The only way that the black hole can lose energy from the stars is if a star actually passes between the two components of the binary and gets flung out in a slingshot from the binary. That means that eventually all of the stars that can interact with the black hole are ejected from the galaxy. So what happens is the decay time starts to go up, and then you enter a long phase in which the decay time is determined by the rate at which the region of phase space in which stars can interact with the binary is depleted, probably by star-star gravitational scattering. And then finally, and thankfully, they get close enough that gravitational radiation starts to be important, and they rapidly spiral in together and merge. So what you see from this cartoon is that there's a bottleneck of a couple orders of magnitude in which the decay time is longer than 10 to the 10th years, longer than the Hubble time, and the question is whether the binary spirals at this stage. This is only a cartoon, but more detailed models, more accurate models using actual galaxies confirm this. This is estimates of a similar decay curve for 2 different mass ratios for 30 or so nearby galaxies, and you can see that there's still a range of several orders of magnitude where the decay time is longer than the Hubble time. A variety of possible solutions to this have been proposed. I won't go through these in detail. One is to try to improve the rate of filling of the lost cone, the region of phase space that can interact with the black hole. It could be from tidal forces if the galaxy is non-spherical, massive perturbers like star clusters or molecular clouds, if the system has a messy center like our own galaxy does. But no matter how much you do, even if the lost cone is kept full, in many cases the decay time is going to exceed the age of the universe. You could have gas drag. One of the troubles with gas drag is that if it's too efficient, it actually accelerates the final in-spiral faster than gravitational radiation, and so there are fewer black holes in the in-spiral phase and a smaller stochastic background. Maybe you can do it if a third black hole comes in to remove energy from the binary. Whatever the answer is, it remains true that the slowest part of the evolution is at sub-parsec scales, and so there should be a big population of sub-parsec binary black holes at the centers of galaxies. And the question is, where are they? The answer is that we have extremely poor evidence for any examples of such systems. There's one binary active galactic nucleus at a separation of 7 parsecs, which is really too big for us, and that's after searching hundreds of galaxies for these objects. You can look, when you have an active galactic nucleus, if it's a binary and both black holes are active, you could see 2 sets of emission lines that are shifted from one another, but there's no clear examples of that. If it's only one black hole is active, the center of the emission line could be shifted from the velocity of the galaxy because of the Keplerian motion of the binary. There's no persuasive evidence of that. Because the orbital periods are short, you could look for drifts in the velocities of the lines due to the Keplerian motion of the binary. Again, there's no clear evidence of that. You could look for periodic variability in the AGN, which might be a sign of a binary period. There have been a couple of claims. This is a famous one called OJ287, which seems to have outbursts every 12 years that might be associated with a binary. There's one here with a period of, which sort of looks like it has a period of 5 years. This one has a period of 1.5 years, but with the parameters they give, this one should, let's see, the paper was in 2015. I think it's supposed to merge next year, which seems a little fast for any reasonable system. You can look for anomalies in the radio jets emerging from these systems. These are called X-shaped radio jets. The idea is that you got the fuzzy one is an old, or the bigger one is an older radio jet, and that then the 2 black holes merged. It changed the orientation, and so they sent out a radio jet in a different direction. So that's a possible interpretation. In these 2 cases, the radio jet seems to be a corkscrew, and so there's some argument that the spin axis of the black hole is precessing due to the presence of another black hole. But the evidence is extremely indirect. So let me summarize. I think it's fair to say that there's no direct evidence that supermassive black holes generally merge. My own guess is that some of these mergers do occur, but the rate at which they occur and the mechanism by which they get through the bottleneck are unknown, and the fraction that occur is extremely difficult to estimate. If you do try to estimate this, it seems easier to overcome the bottleneck in low-mass galaxies, which means low-mass black holes, supermassive black holes at the low end of the mass range, around 10 to the 7th solar masses, are more likely to merge than the high-mass ones. That's good for E-LISA because that's the range it's sensitive to, and bad for pulsar timing arrays because they're most sensitive to the biggest black hole mergers. Whether or not they merge, it's likely that a large fraction of galaxies contain sub-parsec binary black holes, but there's not yet a single convincing case. And although I think the current data are consistent with the rates at which you'd expect to see these binary black holes, I'm starting to get a little worried, and it would be awfully nice to see a few systems where we could really cleanly say that we're seeing a binary black hole that's got an orbital period less than a few hundred years and a separation of less than a parsec. Okay, I'll stop there. Thank you.
If there are these massive black holes, I'm sure they are, but how come
For stars being absorbed by the black holes, the rate is about, expected rate is about 1 per 10 to the 4th years per galaxy. We do see them, or at least we see events that most astronomers are convinced result from this, but obviously at one per 10,000 years, you need to look at a lot of galaxies to see them.
Somehow on this last parsec problem, I understand that all these models have been made without assumption on dark matter. Now, somehow, is there an easy way to understand why dark matter doesn't play a role in this process? Sort of in galactic states, I always thought it's important.
Certainly it is. I think the reason it's not important is that at large distances in the galaxies, at distances of 10, 20, 30 kiloparsecs, the black holes, the dark matter starts to dominate over the baryonic matter. That's because generally the dark matter is much more extended than the baryonic matter. In the centers of the galaxies inside the central parsec, in most models, the mass is dominated by the baryons rather than the dark matter. So because it's so close to the center, the baryonic density is high enough that the dark matter is making a negligible contribution to the total effects on the black hole.
And the spread of the dark matter is just because it's so weakly interacting with anything else?
Right. Basically, if the dark matter is weakly interacting, it has no mechanism by which it can lose energy and sink into the center.
Thank you, Scott, for visiting us and for these wonderful lectures. Thank you.
Thank you.